Hello everyone, my name is Iman. Welcome back to my YouTube channel. Today we're going to continue our lecture on intermolecular forces, and we've made it to the second objective, which focuses on phase changes. Phase changes refer to the transitions between different physical states of a substance, solid, liquid, and gas. These transitions, they occur when energy in the form of heat is added or removed from a substance, and that's going to alter the arrangement and motion of its particles. Understanding these phase changes is going to be crucial for grasping how substances behave under various conditions. Now, there are 6 primary types of phase changes that we want to cover, and we're going to start off with melting. Melting is the transition from solid to liquid. Freezing is the transition from liquid to solid. Vaporization is the transition from liquid to gas. Condensation is the transition from gas to liquid. Sublimation is the direct transition from solid to gas without passing through the liquid phase, and deposition is the direct transition from gas to solid, again, bypassing the liquid phase. Now, these phase changes are driven by changes in temperature and changes in pressure, and they occur at specific points known as the melting point or the boiling point or the sublimation point, etc. The enthalpy changes that are associated with phase changes are going to be really key to understanding the energy that's required or released during these transitions. So, for example, the heat of fusion is the enthalpy change that's associated with the melting of a solid. And the heat of vaporization is the enthalpy change that's required to convert a liquid into a gas. Now, the heat of vaporization of a given substance is generally much higher than its heat of fusion. So think about it like this. When a substance is vaporized, its intermolecular forces have to be completely overcome so that the molecules can be totally separated and they can be in the gas phase. In contrast, when a substance melts, its individual molecules, they're given a greater freedom of motion, but they still remain very close. Therefore, melting only requires sufficient energy to partially overcome intermolecular forces. And that is the reason why the heat of vaporization of a given substance is generally higher than its heat of fusion. Now, understanding these concepts, we want to transition into discussing heating curves. A heating curve is a graphical representation of how the temperature of a substance changes as heat is added. It provides a visual understanding of the phase changes and the energy that's involved in transitioning from one phase to another. Now, in a typical heating curve, the x-axis represents the amount of heat added to the substance, and the y-axis represents the temperature of the substance. As heat is added, the temperature of the substance increases, except during phase transitions. During phase transitions, the temperature remains constant even though heat continues to be absorbed. And this occurs because that energy is used to break the intermolecular forces holding the particles together in the current phase rather than increasing the kinetic energy or the temperature of the particles. So for example, let's consider heating a solid substance. Initially, as heat is added, the temperature of the solid rises until it reaches the melting point. At the melting point, the temperature remains constant while the solid absorbs heat, and this energy is used to convert the solid into a liquid. The amount of heat that's required for this transition is the heat of fusion. Now, once the solid is completely melted, the temperature of the liquid begins to rise again as more heat is added. When the liquid reaches its boiling point, the temperature again remains constant while the liquid absorbs heat and uses that to convert it into a gas. This is represented by the heat of vaporization. After the liquid has completely vaporized, any additional heat will increase the temperature of the gas. Now, the key takeaway from a heating curve is the distinction between temperature increases, where the substance remains in the same phase and its kinetic energy increases. We see that in the following segments in our heating curve. And then phase transitions, where this is the substance changes phase and the energy is used to overcome intermolecular forces rather than increase temperature. And these are the following phases where we see that occur. Now, the total amount of heat that's required to heat a substance through the different phases, this can be calculated using different formulas depending on whether the substance is undergoing a phase change or simply increasing in temperature. So during the segments where temperature increases, so right here, here, and here, we're going to use a specific equation to calculate heat. And that equation is Q equals mc delta T. We saw this equation in General Chemistry 1. Q here is the heat added, M is the mass, C is the specific heat capacity, and delta T is the change in temperature. Now, what about during phase transitions? What equation do we use to calculate heat in these instances? To calculate heat in these instances, we use this equation, Q equals mL, where Q is the heat added, M is the mass, and L is the latent heat, the heat of fusion or vaporization. Now, the specific heat capacity and the latent heat, these are properties that are specific to each substance and phase, and they determine how much energy is required for temperature changes and phase transitions, respectively. By understanding the phase changes and heating curves, we really gain valuable insight into how substances behave under different thermal conditions and how energy is transferred in these processes. With that covered, let's go ahead and jump into a practice problem. This problem asks, what is the total amount of heat required to convert 75 grams of ice at negative 13 degrees Celsius to liquid water at 62.5 degrees Celsius? We're given the specific heat for ice and for liquid water, and we're also told that the heat of fusion for water is 6.02 kilojoules per mole, and the melting point of water is 0 degrees Celsius. Now, whenever you're asked to calculate the amount of heat when a phase change is involved, the first thing you should do is sketch a heating curve. Keep in mind that for a heating curve, the x-axis is the heat added, and the y-axis is the temperature. Now, in our problem, we start with ice at a temperature below its freezing point. Heat is added until we have liquid water at a temperature that's above its freezing point. So the heating curve has the following appearance. Notice that there are 3 sections to our heating curve, and we're going to call this section Q1, this section Q2, and this section Q3. The first step, Q1, this corresponds to heating the ice from its initial temperature minus 13 degrees Celsius to its melting point, which is 0 degrees Celsius. Now, to calculate the heat for this portion, we're going to use our Q equals mc delta T equation. Here, m is mass, C is the specific heat capacity, and delta T is change in temperature. Now we're given the mass. The mass is 75 grams. We're also given the specific heat capacity for ice in the problem, 2.09, and we can easily calculate our change in temperature. Remember that change in temperature is final temperature minus initial temperature. So final temperature is 0 degrees Celsius, and we're subtracting that from our initial temperature, which is 13 degrees Celsius. Plug this into a calculator, and what we're going to get for Q1 is 2,038 joules. Or if you wanted to write this in kilojoules, it would be 2.038 kilojoules. So that is the heat for our first segment, where we heat up our ice up until the melting point. What about this second segment, Q2? So the second portion of the curve, Q2, is flat. It occurs at the melting point. Even though heat is being added, the temperature doesn't increase until all of the ice is completely melted. The additional thermal energy that is added is going to allow all of the solid molecules to partially overcome the intermolecular forces and go into the liquid phase. Now, the equation that we use for this segment is Q equals mL, where m is mass and L is latent heat. Now, latent heat can be our heat of fusion or vaporization, depending on what you're looking at. Here, we're looking at converting solid to liquid, so we're concerned with the heat of fusion, which we are given in this problem, 6.02 kilojoules per mole. Now, looking at our equation, it's mass multiplied by latent heat. And what we have in the end is our heat calculated in units of kilojoules. There's a problem. Our L value here is going to be our heat of fusion, which has units of kilojoules per mole, and our mass has units of grams. So here we're going to have to add an extra step where we convert our grams of water into moles of water, and then multiply the moles of water with our heat of fusion to make sure that our units cancel out appropriately, and we get our heat for the second segment in units of kilojoules. So let's go ahead and write that out. What we have here is 75 grams of water. We want to convert that to moles. We're going to use molar mass. 1 mole of water is equal to about 18 grams of water. Then we're going to multiply this by our heat of fusion, which is 6.02 kilojoules per mole. Notice grams cancel out, moles cancel out, and we're going to get Q2 in units of kilojoule. Plug this into a calculator, you're going to get 25.06 kilojoules. Beautiful, so we've calculated the heat for that second step. Now we're left with our final segment, Q3. So this third step involves heating water from its freezing point to its final temperature. The heat for this step is going to be determined using our equation Q equals mc delta T. Remember, again, C stands for specific heat, and we're given that for liquid water in our question stem. It's equal to 4.18. We're also given the mass, 75 grams, and we can calculate the change in temperature as final temperature minus initial temperature. Our final temperature is 62.5 degrees Celsius for this segment, And our initial temperature for this segment is 0 degrees Celsius. So if we start to plug things into our equation, we have 75 grams multiplied by 4.18, and then that's multiplied by change in temperature, which is final temperature, 62.5 degrees Celsius, minus initial temperature, which is 0 degrees Celsius. If we plug this into a calculator, what we're going to get for that third segment for heat is 19,590 joules, which is also equal to 19.590 kilojoules. So there we have it. We calculated the heat for each of our segments, Q1, Q2, and Q3. Now to calculate the total enthalpy change, we're going to have to sum up the heat we calculated for each of these segments. So we're going to add up Q1 plus Q2 plus Q3, and that sum is going to give us Q total. Now what we're going to do is make sure that they're all in the same unit. So we're going to use kilojoules. All right, so we're going to add up Q1, which is 2.038 kilojoules, plus Q2, which is 25.06 kilojoules. And then we're going to add that with Q3, which is 19.590 kilojoules. And our total is 46.7 kilojoules. And there we have it. We answered this problem. Wonderful. Now we want to move into another really important topic, and that is discussing vapor pressure and boiling point. To discuss vapor pressure and boiling point, it's important to first understand the distinction between the terms vapor and gas. These terms are often used interchangeably, but they do have distinct meanings in the context of phase transitions. A vapor is technically a gas. It shares all of the characteristic behaviors of a gas, such as expanding to fill its container, having particles in constant random motion, and exhibiting a pressure that is proportional to temperature at a given volume. However, the term vapor specifically refers to the gaseous phase of a substance that's normally found in a solid or liquid state at a particular temperature and pressure. In other words, when a substance can condense into a liquid or deposit into a solid under certain conditions, its gaseous state is referred to as a vapor. Water vapor is the gas phase of water, which is a substance that's typically liquid at room temperature. Now, vapor pressure, this is the pressure that's exerted by a vapor when it is in equilibrium with its liquid or solid state. At this equilibrium, the rate of evaporation of liquid molecules equals the rate of condensation of vapor molecules, meaning there is no net change in the amount of liquid or vapor. And this dynamic equilibrium is important for understanding how vapor pressure operates. As the temperature of a liquid increases, more molecules have enough kinetic energy to escape into the gas phase, thus increasing the vapor pressure. Now, the vapor pressure of a substance also depends on the strength of its intermolecular forces. Strong intermolecular forces, such as hydrogen bonds, they're going to require more energy to overcome, meaning fewer molecules can escape into the vapor phase at a given temperature. As a result, substances with strong intermolecular forces have lower vapor pressures. Vapor pressure is also closely linked to the concept of volatility, which is how we describe how readily a substance can vaporize. A volatile substance has a high vapor pressure at a given temperature, and it can easily transition into the gas phase. On the other hand, a non-volatile substance has a low vapor pressure and it does not vaporize easily. The relationship between vapor pressure and volatility is simple. The stronger the intermolecular forces, the lower the vapor pressure, and consequently, the less volatile the substance is. Now let's talk about boiling point. The boiling point of a liquid is the temperature at which its vapor pressure equals the external pressure that's exerted on the liquid. So at this point, the molecules within the liquid have enough kinetic energy to overcome the intermolecular forces holding them together, allowing them to escape into the gas phase. This transition happens not just at the surface of the liquid, where evaporation typically occurs, but also throughout the liquid, leading to the formation of bubbles. These bubbles are pockets of vapor that rise to the surface and burst, releasing the gas into the atmosphere. Now, the boiling point of a liquid is not a fixed temperature. It varies with external pressure. So at higher altitudes where atmospheric pressure is lower, the boiling point of, say, water decreases, meaning it will boil at a temperature lower than 100 degrees Celsius. On the other hand, increasing the external pressure raises the boiling point, allowing the liquid to reach higher temperatures before that liquid boils. So, in summary, understanding vapor pressure and boiling point requires a clear distinction between the phases of matter and the forces at play. Vapor pressure depends on temperature and the strength of intermolecular forces, and that influences a substance's volatility. And then the boiling point is where a liquid's vapor pressure matches the external pressure, and that allows molecules to transition fully into the gas phase. With that being said, let's go ahead and transition into our third objective, where we're going to discuss phase diagrams. In our second objective, we came to understand how heating curves illustrate the energy changes and temperature behavior during phase transitions. Here in the third objective, we want to further expand our analysis by examining phase diagrams. And these phase diagrams, they provide a comprehensive view of the states of matter and their transitions at various temperatures and pressures. Now, in a phase diagram, the x-axis typically represents temperature, and the y-axis typically represents pressure. The diagram is also divided into regions that represent the different states of matter. Here is our solid phase, our liquid phase, and our gas phase for a particular substance. Now, each point on a phase diagram represents different temperature and a different pressure. The various regions are labeled to show the most stable state of the substance under those conditions. So under conditions of temperature X1 and pressure Y1, the most stable state for our substance to exist in is the liquid phase. Now, the lines that you see here, the lines and curves you see here are really important. They demonstrate temperatures and pressures at which two states can coexist in equilibrium. So here I'm going to highlight in blue the solid and liquid phase. The solid and liquid phase is called the fusion curve, and each point on this line corresponds to a temperature and pressure at which the solid and liquid phase coexist in equilibrium. In a similar way, the curve separating solid and gas, this one right here, is the sublimation curve, And the curve separating the liquid and gas right here is known as the vaporization curve. Now, there is one point on the phase diagram where the three curves intersect, and this is called a triple point. It represents the temperature and pressure at which the three phases of a substance, solid, liquid, and gas, coexist in equilibrium. Another important point on the phase diagram is this point right here called the critical point. The critical point represents the highest temperature and pressure at which the substance can exist as a liquid. Beyond this point, the distinction between liquid and gas phases disappear, and the substance becomes a supercritical fluid. A supercritical fluid is neither a liquid nor a gas, but it possesses properties that are somewhat intermediate between the two. The last point I want to make here is that it's important to remember that these phase changes are usually reversible. And with that, we can move into our last and final objective, where we're going to discuss the properties of liquids. In this last objective, we're going to discuss three properties that are indicative of the intermolecular attractive forces holding molecules together in the liquid phase. And those are surface tension, viscosity, and capillary action. Let's go ahead and get started with surface tension. This is a fundamental property of liquids, and it is defined as the energy required to increase the surface area of a liquid by a unit amount. This phenomenon occurs because molecules at the surface of a liquid experience fewer intermolecular forces than those in the interior. Inside the liquid, molecules are surrounded by others on all sides, and this leads to balanced forces and lower potential energy. In contrast, the surface molecules are only partially surrounded, so they experience a net inward pull from the molecules beneath them. As a result, the surface of a liquid tends to contract and minimize its surface area, creating an effect similar to an elastic membrane. This is why water droplets form nearly spherical shapes. A sphere has the smallest possible surface area for a given volume. Now, the strength of surface tension, this is directly related to the intermolecular forces within the liquid. For example, water has a high surface tension due to strong hydrogen bonding between its molecules, which is why small objects like a needle can sometimes float on its surface without sinking. Now, the next thing I want to talk about is viscosity. Viscosity is another important property of liquids, and it is defined as the measure of a liquid's resistance to flow. It describes how thick or thin a liquid is, which depends on how easily its molecules can move past one another. Viscosity arises due to the intermolecular forces within the liquid. Stronger forces create more resistance to flow, making the liquid more viscous. So, for instance, glycerol, which has extensive hydrogen bonding, is much more viscous than water or ethanol. The size and the shape of the molecules also play a role. Larger or more complex molecules can become entangled, which further hinders their movement and increases viscosity. Viscosity can decrease, though, with increasing temperature. And this is because the added thermal energy allows molecules to overcome intermolecular forces more easily, and that enables them to move more freely. This is why substances like honey, they flow more easily when they're warmed up. Now, the next thing I want to talk about is capillary action. And within this branch, I want to talk about cohesion and adhesion and also the meniscus effect. Capillary action is the spontaneous movement of a liquid through a narrow tube or porous material against the force of gravity. So this occurs due to the combined effect of cohesion and adhesion, which are both types of intermolecular forces. Cohesion refers to the attractive forces between molecules of the same substance. So in liquids, these are the forces that hold molecules together, like hydrogen bonds in water. Cohesion is responsible for the surface tension of liquids as well, and it contributes to the rounded shape of liquid droplets that we just talked about. Adhesion, on the other hand, is the attraction between molecules of different substances. So, for example, water molecules are attracted to the glass surface of a tube due to adhesion. When adhesion is stronger than cohesion, the liquid is drawn up the tube, leading to capillary action. This is seen in how water rises in narrow tubes, or how plants draw water from their roots to their leaves. Now, the meniscus, this is the curve that's observed at the surface of a liquid in a container, and it results from the balance between cohesive and adhesive forces. So in a concave meniscus, like you see here, adhesion to the glass is stronger than cohesion between water molecules, causing the liquid to climb up on the sides of the container. In contrast, the convex meniscus, this occurs when cohesion is stronger than adhesion. Like you would see this if you were to put mercury in a glass and the liquid would curve a little bit downwards, like you see in this image. Capillary action is really essential in many natural and technological processes. So in plants, it enables the transport of water and nutrients from the soil through tiny tubes in the plants, tiny xylem tubes in the plants. In everyday life, capillary action is observed when a paper towel absorbs a spill or when ink moves up the nib of a fountain pen. So those are all examples of capillary action. And in summary, the properties of liquids, surface tension, viscosity, capillary action, they're all interrelated and they're governed by the behavior of intermolecular forces. And with that, we've completed this chapter on intermolecular forces. I hope this was helpful. Please let me know if you have any questions, comments, concerns down below. Other than that, good luck, happy studying, and have a beautiful, beautiful day.